Hello everybody, welcome back to my channel where we solve rather difficult integrals. And today's integral is not an integral, it is a series, the series of hn by n squared, where hn is defined here. It is the nth harmonic number, defined as the sum for k from 1 to n of 1 by k. It is not a very difficult series, but quite interesting in my opinion, so we're going to calculate it just in a second. First of all, we know that our series is a convergent series because hn in infinity is known to be equivalent to log of n, and the series of log n by n squared is convergent thanks to Bertrand criteria. So our series H converges, which means we can just go ahead and evaluate it. First of all, we cannot, unfortunately, calculate h just right now, because, well, maybe we can. In fact, I don't really know how, but we can introduce some steps before calculate our series. First of all, we note that we see that here we have 1 by n squared, which can help us to figure out how we can calculate h. 1 by n squared has to lead us to the series development of analytic functions. So our goal is to define some function, let's say h of x, defined as the series for n starting at 1 of hn by n squared times x to the nth power. And this way we can just take the value x equals to 1 and we have our series h. Why should we think about that? Because 1 by n squared can be cancelled just if we differentiate our function h, and if we differentiate twice, we can just get rid of this 1 by n squared and just have and be left with the series of hn times x to the nth power, which will probably be much more easy to calculate and to find a function that can describe the series of hn times x to the nth power if we don't have the 1 by n squared, which is very annoying right now. So how do we do this? We start with the easiest function possible, let's say f of x, defined as the series for n starting at 1 of hn times x to the nth power. We see that hn is defined as a sum, so we have here in fact one series and one finite sum times x to the nth power. And while we don't have any other thing to do, the main idea we have right now is, can we switch up the series operator or the summation operators? Right now, unfortunately, we cannot, because here we have the series for n starting at 1, and here the sum for k from 1 to n of x to the nth power divided by k. And you see that the sum inside of the series is defined using the variable of the series. Here n is a dummy variable, and we use it to define the sum here, which goes from 1 to n. So we cannot just here say, okay, we switch up the series and the sum, because in fact the sum is not defined outside of the series, because the n doesn't exist. If we just have f of x, we cannot define sum from 1 to n of anything, because there is no n. So before switching up the series and the summation operator, we have to change a little bit the function and the way we express this function. It's not very easy to explain, but we can just go right ahead and, well, I'll show you how to switch up the operators here, because because even though the sum is not defined without the series, we can still switch up these operators, but just not right now. So how do we do this? Here we have a series, first of all, a series defined for n, and then a sum defined for k. So we want this to change. We want first to define the whole function thanks to the 1 by k here, the parameter which is not the x to the anything power, and then we want to express another sum or series, anyway, using the x to the nth. So first of all, we have to group the 1 by k in a whole series, and then we will express x to the nth power, which is not the case right now, because first we define x to the first power, for example, and then hn, or x to the second power, and then x to the first power and h1, x to the second power and h2, so on, so on. So f of x right now is defined. For this, we need to do dots, because it's very difficult to just see it if we only use operators. So I will use the development of f of x. For x, obviously smaller than 1, but we don't need any x greater than 1, so not a problem at all. For first of all, we have here n equals 1, so hn equals, well, hn equals here 1, then 3 by 2, so on, so on. We don't really need the values of h of n. Just to see it here, we have 1, we have 1 plus 1 by 2, 1 plus 1 by 2 plus 1 by 3, so on, so on. So we have here 1 times x to the first power. Then we have n equals 2, so hn equals 1 plus 1 half, which I will write 1 plus 1 half, 1 plus 1 half times x to the second power. Plus, I will write one more term, even if we don't really need it. Anyway, h3 is 1 plus 1 by 2 plus 1 by 3 times x to the third power. And then so on, so on. So you see that first the function is defined for the power of x, and then the coefficient in front of it. We need to change that simply by writing our function first defined by the coefficient here, 1, 1, 1 half, etc. And then define and then writing the x to the anything power. So how do we do this? We note, we just look at what coefficient do we have. First, we have 1 here that we see here, 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 and we would see it for the x to the fourth power, and so on, so on. Then we have the 1 half, which appears with the x to the second power, but remains in the x to the third power, x to the fourth power, and so on, so on. Then we have the 1/3, which appears with the x to the third power, but will remain with the x to the fourth, x to the fifth, and so on. So we just write what we see. First, we have 1 times x plus x squared plus x third plus so on, so on. Then we have 1 half. 1 half, which appears with x to the second power, so we don't have any x. X squared plus x third plus so on, so on. Plus, then we have 1/3. 1/3, which appears with x to the third power, but remains with the x to the fourth, so just we will write so on, so on. And then we have again so on, so on, because we have 1/4, we have 1/5, and so on, so on. So now we have a new series which is exactly the same function, because these operations are totally durable, because the series is convergent. If we say that x is smaller than 1, this is absolutely convergent, so we don't have any problem with doing this. Now we just write our function f of x as we see it, and you will see that we have a totally different way to write our function, which is much more useful in order to express it with elementary functions. First, we have a series for n, let's say n, starting at what? Here we have 1, we have 1/2, we have 1/3, 1/3. What is the pattern? We have 1 by n, and here n starts at 1. So we have 1 by n, here not 1 by 1, 1 by n. We have 1 by n, and then we have another series, because here x to the anything power is infinite. So we have a new series, let's say k, starting at, well, it may be a bit difficult, so I will just leave a space here. K starting at anything, and we have x to the anything power. The anything here, you see that k will just goes from 1 to 1. At every step here, k grows to of 1, and here the power of x grows of 1. So we have here k plus something or minus something, but we don't have any 2k or 3k or anything. Or negative k, or we could have a negative k, but not here. We just have k plus something, and what is this something? It is something which depends on the value of the dummy variable, the first one, n. Because here you see that when we have 1, which can be written 1 by 1, we have x to the first power as the first power of x. Here we have 1 by 2, and we have x to the second power. Here we have 1 by 3 and x to the third power, so we have our pattern. We have here x to the k plus n power. Because now you see that we have a series. Here we have a constant, maybe 0, maybe 1, anyway, we don't know for now. You have the pattern. When you have defined this 1 by n, which is the coefficient here, you have the series of x to the k power, and you have to multiply by x to the nth, because here you see that the coefficient I mean, which is in fact the x to the anything power, the first power of x grows when the coefficient decreases. So you have here x to the k plus nth power, and here you have a constant. K starts at a number, not the k starts at a number which does not depend on the value n. So you can just test what value this has to be. So you just take the easiest value n. You have here n equals 1. Here k equals, we don't know, and here equals 1, and we have the first power, which is 1. So here k has to be 0 as our first value of k, and this series, this double series, is exactly our function f of x. And you see that it is a completely different series, because now you define first the coefficient before the power of x, and then you define a power of x. But now this series, these series can be expressed as elementary functions. How? We know that we can just here we have n absolutely everywhere. So first we try to isolate the k variable. So here we have x to the nth power. We'll just put it outside, x to the nth in front of the second series. So you have the series of x to the kth power for k starting at 0, and this is nothing but 1 by 1 minus k, 1 minus x, I mean. So you have 1 by 1 minus x times the series for n starting at 1 of x to the nth power divided by n, which is nothing but negative logarithm of 1 minus x. So our function f of x is log of 1 minus x divided by x minus 1. So now we have our function f of x, and we want to get our function h, which will be much more useful because we need the value in 1, and you see that the value in 1 of f of x is absolutely not what we're looking for, and even here it's a divergent series. So anyway, this is not very useful for now. We need to change a little bit our function f of x, and for that we need to think about integration. Let's get back to the first definition of our function f of x, which will be very useful right now. You see that f of x is the series of hn by times x to the nth power. We want to change this. We want to have some 1 by n to appear, and then we will have 1 by n squared because we will do the same operation once again, but for now we just need 1 by n to appear. How do we do this? We have to think about integration because we have the power of x here that goes to the denominator of the fraction, and you have here the power of x which changes. So if we do it just right now, we have x to the n plus 1 instead of x to the n, and the new power, n plus 1, becomes the denominator. So this is not what we want. We want x to the nth, and even more important, 1 by n, not 1 by n plus 1. So we can't do it right now. We first have to divide our function f of x by x here, and the power of x in the series becomes x to the n minus 1. And then when you integrate, you will have x to the n minus 1, which becomes x to the nth again, and then 1 by n, which appears. So f of x equals log 1 minus x divided by x minus 1. And here it's not f of x, it is f of x divided by x, obviously. And now when we integrate, we get this function here, x to the n minus 1 becomes x to the n, and we have 1 by n. So this equals the series for n starting at 1 of hn by n x to the nth power. So now the question is, how do we integrate f of x by x? So we just integrate log 1 by 1 minus x divided by x minus 1. So let's call this function g of x, because between f and h, why not g? Anyway, g of x is defined as this integral, and to calculate it, we see that we first we have to think about simple elements decomposition. So we have 1 by x minus 1, which can be changed. We want only 1 by x and 1 by x minus 1, which will be very much easier to use. So first, 1 by x minus 1 is, okay, here we have 1 by x, we have 1 by, well, x minus 1 is usually not so useful, so we will just here say 1 minus x. Because the space between those two is 1, we have here 1 and 1, and we have probably a sum, well, but in, okay, we have a sum, but in infinity this is positive, and this is negative, but greater in absolute value than this, so we have here negative and negative. Did I make a mistake? No, it's okay. So we have here g of x, which is the entire derivative of negative log 1 minus 1, 1 minus x, divided by x, minus logarithm 1 minus x, divided by 1 minus x, dx. So this function can be integrated using polylogarithm. Just to say, here we define the polylogarithm as polylog of n plus 1 of x is defined as the entire derivative of polylog n of x by x dx with polylog n of x of 0, of 0 is always 0, because when we do entire derivative we need a integration constant, and polylog 0 of x is 1 by 1 minus x. So the polylog at the first order is the entire derivative of 1 by 1 minus x. Oh right, okay, I made a mistake. This doesn't work. Polylog 0 of x is x divided by x divided by 1 minus x, and then when you divide by x and you integrate, you get polylog at the first order of x equals negative log of 1 minus x. You also have the formula for x smaller than 1 in absolute value. Polylog n of x is the series for k starting at 1 of x to the kth power divided by k to the n power. These two polylogarithms are the only one which can be written in terms of elementary functions. All the other orders are very difficult or just impossible. So here, these are the two you have to remember, and the other ones, you just remember that it's always the entire derivative of the other one divided by x. Well, anyway, and you have the relation polylog n of x is always zeta of n for n greater than 1, obviously. Well, greater or equal to 2. So here we have the polylog at the second order x of x, which is called the logarithm of x, is the entire derivative, well, the integral from 0 to x of log 1 minus t divided by t dt. We have a negative sign here because the dialog is positive for positive arguments. So here we just have the logarithm. So g of x equals dialog of x minus this integral, minus the integral from, well, we don't have an integral, minus the entire derivative of log 1 minus x divided by 1 minus x. And when we have the same argument in the logarithm and the denominator, we cannot use that polylogarithm. We have to use usual functions. And here we have to think about u substitution. Here the argument of the log is just the new value, let's say u. So here this is u as well, and you have to change the dx, which becomes negative du. So here we have the negative, so we have a positive here, entire derivative, logarithm of u divided by u du, and this is obviously the logarithm of x. Here we have logarithm squared of u divided by 2, logarithm squared of u divided by 2, and we have our integration constant plus c. Just to remember, u equals 1 minus x, so now we can get back to our x variable. G of x equals dialog of x plus log squared 1 minus x divided by 2, and here we have our integration constants plus c, which we can calculate very easily. We take the easiest value x. Here x equals 0 because g of x is defined as a series of x to the nth power and n starts at 1. So we have here g of 0 equals obviously 0. And we have here the logarithm of 0 is 0 because the polylogarithm of 0 is always 0. And we have logarithm squared of 1 minus 0, which is log squared of 1, so 0 as well. So the c constant here is nothing but 0. So now we have our function g of x. And we have to integrate it again because this is the series of hn by n x to the nth power. So we need to get 1 by n again, which will make 1 by n squared. So we have to do these, well, the same thing. We divide by g of x by x and then we integrate. So let's say, well, we already have it, h of x here. So, alright, h of x is the entire derivative of g of x by x dx. Okay, we know it. So we have the entire derivative of dialog x by x, and well, you already know how to integrate it if you listen right now. We have a polylog n plus 1 of x, which is the entire derivative of polylog x by x. So here this is nothing but trilogarithm. Well, the polylogarithm for the third order. So you have a trilog of x, but anyway, here and here plus log squared of 1 minus x. By 2 dx. And this is not very easy to handle because log squared of 1 minus x is not very, oh, I forgot this x here. We have always divided by x. It will be much easier. Or maybe it won't, I don't know. Okay, how do we do this? Well, this is not, probably not obvious, but here, we have to think about the IDP because we want to differentiate log squared of 1 minus x because in fact log squared is very not useful and we absolutely need to have logarithm at the first order because else we won't be able to integrate it ever. So we need logarithm to the first order, so we have here to integrate 1 by x, which becomes logarithm of x. And here differentiate log squared of 1 by x, so we will have 1 by x in the denominator, and we will have logarithm 1 by x, and it is much easier to have log x times log 1 minus x than just log squared 1 minus x. So, okay, this is, we set it trilogarithm of x. Plus here, so alright, we have, this is plus, not an equal. First we have the brackets, so we have the entire derivative of this and the entire, this function and the entire derivative of 1 by x, so log x by 2, let's say this way, log squared 1 minus x. And then we have to be very careful. Because we have the chain rule here, we have the negative because of the IDP, and we have the 2 here and the 2 here because the power of log becomes the coefficient of multiplication. So we have here minus, so plus the entire derivative of logarithm 1 minus x divided by here 1 minus x log x dx. And I'm pretty sure I didn't make any mistake here. If you're not sure that everything is right with the logarithm, just put the absolute value here and say that logarithm 1 minus x is nothing but logarithm of absolute value x minus 1. This way it's very easy because you have x minus 1 at the denominator, and you don't have any chain rule because, well, the chain rule, the derivative of the inside is just 1. If you have x between 0 and 1, the absolute value has always its derivative, being 1 and never -1. So it's easier this way, but well, anyway, we can do it without absolute values. So first we have this function between brackets, and while this is a entire derivative, we don't need the brackets. So we have trilog of x plus log x log squared 1 minus x divided by 2. And now we have this hell of an integral, I would say. First of all, we have to think about, okay, if I do an IBP, it's not possible because I just did one, so this is not very helpful. So we have to think about, maybe we can do an IBP, but first we have to do a substitution. So the substitution here, I don't really see anyone else than just here 1 by x being the new argument, the new variable. So let's say 1 minus x equals t. So x equals 1 minus t, and dx equals negative dt. So here we have negative dt. We have here log 1 minus t, and we have here log t by t. So we have the negative with which comes in front of the entire derivative. So negative entire derivative of log t divided by t logarithm 1 minus t dt. And now it's not very obvious. We will do an IBP, but we have here 3 functions. We have log t, we have 1 by t, and we have logarithm 1 minus t. So we have to know which function comes with the other one to do the IBP, and is it the entire derivative or is it the derivative? So we just have to test. If we do logarithm times logarithm, it's very complicated because, well, if you integrate, I don't even know how the hell you want to integrate log t times log 1 minus t. So this is not an option. Maybe you can differentiate, but we have the product rule, so well, it will be very, very difficult, and you have much more in the entire derivative than what we have now. So not a real option. So you have to split the logarithms. One is the entire derivative and one is the derivative. So here we have log t by t, and it's not very useful right now because you cannot differentiate. It's very difficult to differentiate log t by t. It won't be any useful in the end. And well, if you try to integrate logarithm 1 minus t, it will be even more horrible, so not this way. And if you integrate log t by t, you get logarithm squared of t, well, with a factor, we get with a coefficient 1 by 2, but well, doesn't matter. And here, well, okay, maybe the 1 by 1 minus t can be solved using power series and gamma function, but very not the easiest option. So clearly the only group we still have here is here. I will write it just another way. We have plus the entire derivative of logarithm t logarithm 1 minus t divided by negative t dt. And now maybe you see it here, we can differentiate, we get 1 by t, and here we can integrate, we get the logarithm of t, and then it will be very useful. So here we have well, this we know what we have. We have first the entire derivative of both. So here we have log t times dilog t, and then you have minus, well, you have to differentiate log t, so minus dilog t divided by t dt. And here the bracket is not very useful, not more than these ones. So we have equals logarithm, and t is nothing but 1 minus x. So logarithm 1 minus x, dilogarithm 1 minus x. And here we have minus trilogarithm of t, which is trilogarithm of 1 minus x. And we have our iteration constants plus c. Again, it is a new c, but anyway. So we have finally our function, h of x. Here this is h of x, not d of x. H of x equals trilogarithm x plus log x log squared 1 minus x by 2 plus logarithm 1 minus x dilogarithm 1 minus x minus trilogarithm 1 minus x plus c. And now we need to evaluate our integration constant c. So again, we can just use the special value x equals 0, and it will be very, very easy. So I won't do any limiting case like which goes to infinity. Is it fast enough to go to a constant, or just it's always vanishes? It always vanishes, because with logarithms you can be pretty sure that every time you have infinity it will just cancel out. So if you let x being equal to 0, here you have logarithm 1 minus x, which is equivalent to 1 minus x when x goes to 0. And so when not 1 minus x, it's equivalent to negative x. So when you multiply negative x squared, because you have the squared here, times logarithm of x, this is equivalent to x squared times log x. It always vanishes. Well, it vanishes as always, so in 0 this doesn't matter. Trilogarithm of x is 0, because polylogarithm of 0 is always 0. So this vanishes, and here you have logarithm 0 times dilogarithm 0. But what am I saying? No. Here we have x equals 0, so logarithm 1. The dilogarithm is finite, and the logarithm 1 is 0, so this vanishes as always. And here you have negative trilogarithm of 1 minus 0, which is finally anything else than 0. You have negative zeta 3, because remember, polylogarithm at the nth order of not x1 is nothing but zeta of n, with zeta the Riemann zeta function. So negative zeta 3 plus c equals 0, because it is h of 0, which is by definition 0. So here c equals zeta 3. So now we can calculate our series h, which is little h of the value 1. We do it right now. H of 1 equals, well, pretty much the same, always 0, or as much as we can. Here we have trilogarithm of 1, which is zeta 3. Here we have logarithm of 1, so 0, because here we have log 0, but again it doesn't go to infinity fast enough to compensate here the 0, so this is 0 again. Here you have logarithm of 1, logarithm of 0 times dialog of 0, but dialog is equivalent to x when x goes to 0. Well, here x goes to 1, but this x is not the same. Well, here let's say it's the value t, with t being equal to 1 minus x, and t goes to 0, so we have this goes faster to 0 than this to infinity, so this vanishes again. And here you're left with minus trilogarithm of 0, which is 0, and you have our constant plus c, which is zeta 3. So plus 0 plus 0 plus zeta 3, and you're left with twice the Paris constant, zeta 3. So the series for n to negative 1 of hn by n squared is nothing but 2 zeta 3. Fuck. I hope you enjoyed the video, which was, as usual, much longer than what I expected, so... Well, I hope you understood everything I explained right now. It was a interesting series, but, well, okay, not very useful, as usual, as any rules. Next time we will meet again, maybe to evaluate the alternating series here with the same series pretty much, but with a negative 1 to the n minus 1 power, which can be linked to the zeta 3 Paris constant, as usual, you know, but it uses complex analysis and the complex values of the logarithm, so, well, I'm not so sure I will do it. It is very, very difficult and not so much interesting, so I don't think I will do it. So I'm pretty sure the next video we will evaluate a interesting integral, as usual, as always. It's the integral, not a series, the integral from 0 to pi halves of logarithm squared of tangent theta d theta, and it's a horrible integral. I have to say it's very, very, very horrible, but okay, why not? Until then, study, learn, and progress. See you next time.